Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets Review for May of 2022. So, I just got back from the American Astronomical Society conference in Pasadena. This was the first in-person meeting since January of 2020, and it went really well. There was a lot of interesting science discussed there, although, as with Exoplanets 4, I'll leave that for other people to explain. There are always great commentaries and live tweets about it, so you can check those out. And in fact, I didn't even go to that many Exoplanets talks there, because I felt like I had caught up with a lot of the latest science at Exoplanets 4, so while I really enjoyed it, it was not quite as relevant to this series. As always, I will be discussing the latest Exoplanets papers, listed as preprints on archive.org in the month of May. So let's get started. We did have some interesting exoplanet discoveries last month. The first one was Ross 508b. This is a potentially habitable planet orbiting a red dwarf star, kind of like this one. It was discovered by the Subaru telescope on Mauna Kea in Hawaii. It's about 4 times the mass of Earth. It gets about as much sunlight as Venus, which is kind of borderline for habitability, but there are conditions in which a Venus-like planet can be habitable, and especially with a red dwarf, the thermal properties of the spectrum are different, so I think it's a little easier under those conditions. However, this is a radial velocity planet, so we don't know its radius, and therefore we don't know whether or not it has a solid surface. So potentially habitable is just based on mass and temperature in this case. The next interesting planet was WASP 132c, and this is a hot super-Earth that orbits very close to its star, and it's interesting because it's an inner companion to a hot Jupiter, WASP 132b. And that's interesting because with hot Jupiters, we expect they migrated into their close orbits, and so would be likely to kick out any other planets that are nearby, but some of them do have these inner companions, suggesting potentially a different formation pathway. WASP 132c has an equilibrium temperature of 1500 Kelvin, which is about the temperature of molten lava, so it probably has a molten surface. But the other interesting thing about it is that its radius is smack in between the range for super-Earths and mini-Neptunes. So it's not clear whether or not it has a thick hydrogen atmosphere, or if its atmosphere is in the process of being lost. So further study of this object is definitely warranted. And third, this one isn't exactly an exoplanets paper, but I'm going to bend the rules because it's an interesting parallel. This is a scaled-up planetary system around a supernova progenitor. In other words, a high-mass star. And this is Mu-2 Scorpii. Not the Pokemon, but the Greek letter mu. These images were taken by the Sphere instrument on the Very Large Telescope in Chile. And Mu-2 Scorpii is a type B2 subgiant of 9 solar masses. And that's already pretty interesting because we don't see many planets around high-mass stars. Part of that is because high-mass stars don't live very long and planets take time to form. So for the highest mass stars, they just don't live long enough to have planets. 9 solar masses lives long enough, but it's still pretty far outside the norm of where we're even looking for planets. But Mu-2 Scorpii has 2 brown dwarfs orbiting around it, in orbits similar to our outer planets. And if you scaled the whole system down to the size of our Sun, these would be roughly Jupiter-sized planets. And given those masses, and especially those mass ratios and their distances, it's plausible that these planets formed in the same way as giant planets like Jupiter, by the same processes. But current models of planet formation still struggle to produce those kinds of objects, so they're still in need of refinement to figure out exactly what's going on. As always, we move from individual planets to studies of planet populations, and there was one interesting paper I saw last month: a dearth of close-in planets around rapidly rotating stars, or a dearth of data. And this is based on the population observed of close-in planets around rapidly rotating stars, which usually means young stars, but not always. And this is a plot of planets in orbital period versus stellar rotation period. The black dotted line is a 1-to-1 ratio. And up until recently, there have been very few planets discovered that were close in with orbits of less than about 5 days around stars that were rapidly rotating with rotation periods of less than 5 days. And one theory about this was that for a rapidly rotating star at a close-in planet, tidal forces would become a major factor and either push the planet outward if it orbits more slowly, kind of like our moon, or if it orbits more quickly, it could actually pull the planet into the star, like Mars's moon Phobos. And this was an interesting theory, but the latest analysis with the larger sample of planets from TESS suggests maybe we just didn't have good enough data. Because TESS has found a fair number of planets in this corner of the plot. Not as many as farther up, but there aren't that many planets in that close anyway. And in fact, there's not that many fast-rotating stars to begin with. So this suggests that there's not anything too remarkable about this corner of the parameter space, we just weren't looking close enough. Continuing on, there were some interesting results on planet formation, particularly comparing observed populations of planets with formation models. And this first paper, RV Detected Planets Around M-dwarfs, Challenges for Core Accretion Models, specifically looked at the distribution of planets around low-mass stars. And what they did is they generated a model population of planets in blue and compared it against observed planets in red, number of planets versus planet mass, and they compared the results for solar-type stars and low-mass stars. And the interesting thing is the models predict that low-mass stars should have very few giant planets, planets of even larger than Neptune mass, as you can see from the blue line in the middle panel. But we've actually observed a fair number of giant planets around low-mass stars. And this is surprising, because the simple first-order models say low-mass stars have less material around them to form planets, so you would expect few to no giant planets, but we still find a few. So that is an interesting result that suggests we may need to revise our formation models. Next, we have a paper that I think makes a rather bold prediction. Properties of the radius valley around low-mass stars, predictions from the core-powered mass loss mechanism. And this is the latest of many papers modeling the radius valley in the exoplanet population, in between planets that are rocky and those that have a thick hydrogen atmosphere, which adds significantly to the radius. In between them, there's a gap of planets where the observed radius would require a hydrogen atmosphere that's too thin to be stable. It would evaporate away too quickly. And again, this team's model compared low-mass stars with solar-type stars, but this time they focused on the very lowest mass stars. Or rather, they looked at the full range, but the most interesting result was for the lowest mass stars. Not just red dwarfs, but the very small TRAPPIST-1 type red dwarfs. And they predicted, essentially, that the mass loss rate for red dwarf planets would be smaller. Now, this is not due to photoevaporation. This is the core-powered mass loss mechanism, which is essentially thermal evaporation of the atmosphere just because of its temperature. But red dwarf planets are less irradiated, so that's still going to be slower for the lowest mass stars. And they make a rather surprising prediction that for the lowest mass stars, the radius valley will be all the way down around 1 Earth radius. So planets down almost to Earth size will retain thick hydrogen atmospheres around the lowest mass red dwarfs. And for one, this would have major implications for the TRAPPIST-1 planets, all of which are pretty close to Earth size. But for another, will be very clear in the population statistics once we observe enough red dwarf planets, for example with TESS and other upcoming missions. Because for Sun-like stars, we know that the radius valley is up around 1.6 Earth radii. So that's a very significant difference and will be easy to test once we observe enough planets. Related to that, we have what I think may be an even bolder claim, evaluating the evidence for water world populations using mixture models. And this is an ongoing debate that has gone back and forth in the exoplanet community. You see, back in 2017, 5 years ago now, B.J. Fulton did a survey of Kepler planets, measuring masses for as many of them as he could with the California Kepler survey. And he looked at the mass radius distribution he found and concluded that water worlds that have a very high water content, tens of % water by mass, are rare to non-existent. In fact, if you just look at the observed radius distribution, there are 2 peaks, one down around Earth size or a little larger, which are rocky planets, and another at greater than 1.6 Earth radii, generally up around 2 Earth radii, that have hydrogen atmospheres. If there were water worlds that are 50% water, like the outer solar system moons, they would tend to fall right in that gap. And because that gap is relatively empty, B.J. Fulton predicted that there probably were not any water worlds, at least for the close-in Kepler planets. But in the past, maybe only just a few months, there have been other papers challenging that. Like this one, by Andrew Neal, Jessica Liston, and Leslie Rogers, building population models with different planetary compositions and different combinations of compositions to see which ones best reproduce the observations. And they looked at 10 different models that included different combinations of planetary compositions. So, pure rock planets, pure ice planets, rock with a hydrogen atmosphere, ice with a hydrogen atmosphere, rock-ice mixtures, and evaporated cores, which are planets that used to have hydrogen atmospheres, but they were evaporated away. Now, in my personal opinion, some of these models are more likely than others. For one, any model that doesn't include pure rocky planets, I think can be pretty quickly eliminated, because after all, Earth is a purely rocky planet. The water content of Earth is 0.01%, so that doesn't really count for these purposes. And also, I think it's pretty unlikely to have an intrinsically rocky planet without a corresponding rock plus gaseous envelope planet, or vice versa, or the same for ice. So, any models that don't include those parallels also seem rather unlikely to me. That leaves 3 of the 10 models that are especially worth looking at. But, as makes sense to be more thorough, this team looked at all 10, calculated the distribution of planets produced with each composition, plotted them on the standard radius period chart, and then plotted the distribution of radii. And of the 10 models, some of them produced the observed distribution of radii better than others. Model 3, which included all and only the rocky compositions, does seem to fit the data. But also, so do Model 4b, and most interestingly, Model 6, which include all of them. And this is somewhat surprising. Model 6 isn't the best, but it still fits somewhat well. Certainly still has the 2 peaks, and this seems to be because the intrinsically icy planets are larger than originally thought. They don't fall in the gap, but rather above it. And the evaporated icy cores are quite low in number. So where they might fall in the gap, there aren't enough of them to make that much of a difference. It's not a perfect fit, and more work needs to be done, but it does suggest that you could have a significant population of icy planets or water worlds, where we previously thought there would not be any. So I'm excited to see what developments are coming up in that area. Next, there were some interesting papers about planetary system dynamics. Here's one with a fun title: The Great Planetary Heist, Theft and Capture in Star-Forming Regions. And this is based on the fact that most stars form in clusters, where they start out quite close together. And when stars are closer together, they can have closer encounters where their gravity disrupts planetary orbits, and it's much more likely for a planet to get thrown out of the system or even stolen by another star. and start orbiting a different star from the one where it formed. And so this team did a bunch of computer simulations of planetary orbits in a star cluster to see what kinds of trajectories for these planets were most likely. And they looked at 4 possibilities: the one where the planet was preserved around its original parent star, one where it was stolen by another star, one where it was kicked out of the system and became a free-floating planet, and finally, the case where the planet is captured, which is not quite the same as stolen because it's kicked out of the system first and spends some time as a free-floating planet before being captured by another star, so it's not directly stolen. And you can see from the plot that apparently thefts are most likely to happen pretty early, in just a few tens of thousands of years, while stolen planets take a bit longer, a couple 100,000 years. And both of them are rather less likely than free-floating and preserved planets, but there are still significant numbers. And what I think is more interesting is the orbital distance distribution predicted by these models. Because in all of the models, there's a cutoff at a few tens of AU, beyond which planets are unlikely to be preserved around their original stars. And this is a little confusing. It's a cumulative distribution plot. So the sharp vertical movement in the black and gray lines, preserved planets, means that nearly all of the preserved planets fall closer than that radius, and actually at about the same radius, in fact. Meanwhile, stolen planets should fall over a wider range of orbital distance, and captured planets across an even wider range, which can extend to larger distances, hundreds or even thousands of AU. And the really interesting thing is that the observed population of directly imaged exoplanets seems to follow the captured planets curve. So this would suggest that the directly imaged planets that we're observing at these large radii, perhaps unsurprisingly because planet formation isn't expected to extend past about 100 AU, may in fact primarily be free-floating planets that were captured from the birth cluster, as opposed to planets simply being scattered to wider orbits. So that definitely merits further investigation, because that's quite significant challenge to our previous models of planet formation. Next, we have exomoons as sources of white dwarf pollution. And this is one of those papers that's a very simple question to ask, but no one had really looked at it before, and it gives a surprising result. So white dwarf pollution is a situation where white dwarfs that should have mostly hydrogen and helium atmospheres, or carbon and oxygen, depending on the circumstances of their formation, actually have a lot of metals in their atmospheres like iron and silicon and aluminum and magnesium. And you don't expect to find those in a white dwarf just because of how stellar evolution works. And this has been known for a long time, and the theory is that fragments of planets or asteroids that survive the red giant phase of the star fall onto the white dwarf and pollute its atmosphere with metals. And this is a very straightforward theory, except that the usual theory is that it's asteroids doing this. Well, this team, led by Isabella Trierweiler, calculated the mass of metals in some of these white dwarfs, and found that in many of them, it's actually too large to be caused by asteroids. Here's a plot of potential impactor masses for the different white dwarfs, and the mass of Ceres, the largest asteroid, is down here. The mass of Pluto, the largest Kuiper Belt object, is still below most of them. Now, the mass of our own moon is up at the top, but most moons are smaller than ours. So it seems as if a lot of this white dwarf pollution is caused by fragments the size of a large moon. Now, whether this is actually caused by exomoons or just by chunks of planets that have been ripped apart by the star's gravity is not clear. Honestly, I'd put my money more on the planets, but it's an interesting result that should change the way we think about these polluted white dwarfs. And then we have a study of the relative habitability of exoplanet systems with 2 giant planets. Now, Our own solar system has 2 giant planets, so you'd think it would be quite reasonable to think that systems with 2 giant planets are habitable. But Bailey and Fabrici here decided to take a closer look. Because the main pitfall that can happen if you have 2 giant planets is if they wind up in a 2-to-1 orbital resonance. Because with an orbital resonance, gravitational tugs always happen in the same direction, and that can throw the orbits of the entire solar system out of whack. And in fact, many models of the formation of our own solar system suggest that Jupiter and Saturn briefly passed through this 2-to-1 resonance. And it was enough to throw the solar system pretty heavily out of whack. Uranus and Neptune, we think, switched places, and Neptune scattered most of the much more massive proto-Kuiper belt into the Oort cloud. And those kinds of interactions could just as easily upset the orbits of the inner planets, which would definitely cut down on habitability. Question is, are there other failure modes in systems with 2 giant planets? And Bailey and Fabrici looked at it and found nothing all that surprising. If you have 2 giant planets that aren't very close together, like Trojan planets, and aren't in a 2-to-1 resonance, then they don't have that much impact. It matters a little, but not that much. The majority of the systems are still habitable. Now, if you look at the first panel, if one of the 2 planets is at 1 AU in an Earth-like orbit, that's going to prevent an Earth-like planet from occurring there. If the planets have very eccentric orbits, where they would cross the orbits of other planets, that's not good. In the 5th panel, this is actually orbital inclination measured in radians. I hadn't seen that before. It's pretty much always measured in degrees in my experience. But the main thing is, if you have a highly inclined planet, because inclined planets have weird tidal interactions, then it's likely to disrupt the orbits of Earth-like planets, so that's not good. But none of that's all that surprising. And the main thing is, having a second giant planet isn't that different from only having one. So that's a good sign for habitability. Speaking of habitability, there were a couple of interesting papers that discussed that more directly. The first one discussed how oxygen levels might evolve on Earth-like planets as a function of axial tilt. And what Barnett and Olson essentially did was to model Earth with different axial tilts and calculate how much oxygen was produced by the life on Earth, especially phytoplankton in the ocean. And they found that a higher axial tilt, in fact even higher than the one we have today, is potentially beneficial. And this is for 2 reasons. One is that with a low axial tilt, the poles are more likely to be frozen. So a high axial tilt, no polar ice caps, there's more ocean surface to produce oxygen. And second, with a high axial tilt, even the polar regions will have warm summers. And in warm summers, phytoplankton in the oceans will produce more oxygen. And with these 2 factors combined, they found that planets with a high axial tilt, perhaps as high as 45 degrees, a planet could produce even more oxygen and potentially be more habitable than Earth. This is something we call super habitable planets, and it's very much a speculative area of study, but there are a number of factors that suggest it could happen. Next, we have a paper from Sarah Seeger's group about the possibility of detecting life in the atmospheres of sub-Neptunes. And life on sub-Neptunes is something that I have speculated about, not in a paper, but in general. I might make a video about it down the road. It's something that scientists have speculated about in papers, going back to Carl Sagan in the 1970s. He was looking more at gas giants like Jupiter, but sub-Neptunes have a major advantage in that they have denser atmospheres with more heavy elements. More heavy elements means it's easier for life to begin in the first place there, and denser atmospheres means it's easier for life to float with no solid surface to the planet. And the reason this team says that life might be detectable is because life on Earth preferentially uses carbon-12 over carbon-13. Carbon-13 is a stable isotope of carbon, but it's much rarer, and it's not used by life as much because it has slightly different quantum properties. And those quantum properties also mean it has a slightly different spectrum that can be observed in transits. So if there's less carbon-13 used by life, it could be enriched in the atmosphere, where it gets left behind by life, and that could potentially be detectable from Earth, they found. There are certain wavelengths where 13 CO2 would have a noticeably different spectrum than 12 CO2, and the James Webb Space Telescope isn't going to be able to see that. The next generation of space telescopes might be able to, but there's one big problem, which is that it would be basically impossible to tell apart from physical processes changing the isotope balance of carbon. So it's an interesting thought experiment, but probably not that useful in looking for life. And finally, as always, we have the most fun papers from last month, where astrophysicists like to study the more speculative and exotic scenarios for what could happen or what we could discover. And this first one's actually not that speculative. It's something that is very likely going to happen in the 2030s, which is Bayesian characterization of circumbinary exoplanets with LISA. LISA is the Laser Interferometer Space Antenna, a space-based gravitational wave observatory that is planned to launch in 2037. LISA is designed to detect binary supermassive black holes by their gravitational waves, but it will also detect things like white dwarf binaries in our own galaxy that produce similar signals. They're much weaker signals, but they're also much closer. And if those binary white dwarfs have planets, then timing variations in those signals could indicate the Doppler motion of those planets. This is similar to the pulsar timing method that detected the very first exoplanets in 1992. And this group modeled the expected distribution of white dwarf binary planets and determined that LISA might be able to detect about 30 of them, which would be impressive for an observatory that's designed to detect binary supermassive black holes. Also along the black hole lines, we have capture of primordial black holes in extrasolar systems. This is based on cosmological theories that predict that in the early universe, microscopic black holes may have formed from density fluctuations, back when everything was operating down at quantum scales. These primordial black holes are predicted to be very bright due to Hawking radiation as they evaporate, and lower masses are significantly brighter. And just like any massive objects in the universe, they could be captured into orbit around stars, just like the free-floating planets I mentioned earlier. So since they could be orbiting stars and could be bright enough to detect, could we find them in exoplanet surveys? And this team modeled that question, looked at the plausible population of primordial black holes, and they said we probably could if the numbers are especially convenient. There would have to be so many primordial black holes out there that they would equal pretty much all of the dark matter, which is possible, but is not the way dark matter is usually modeled. And they would have to fall in a fairly narrow mass range where they are a little bit larger and less bright, so that we haven't seen them yet. So that's something that will probably be ruled out by next generation planet surveys. But it's a very interesting possibility. And finally, we have transfer of rocks between planetary systems, panspermia revisited. This is by my colleague at University of Michigan, Fred Adams, who's always good for fun speculative papers like this, along with his grad student, Kevin Napier. And if you're watching this video series, you may know about panspermia already, but it's essentially the theory that life can spread from planet to planet, and even from star to star by hitching rides on asteroids and comets. So life forms on one planet, gets blasted off the surface by an asteroid impact, flies through space, and lands on another planet. And the idea is this could explain the quote-unquote surprisingly early origin of life on Earth. Life arose on Earth very early in the planet's history, especially very early in its geological history where it was amenable to life. So perhaps it's more plausible to think that it arose somewhere else first, taking longer to do so, and then came to Earth. Now, usually this is modeled going from planet to planet, especially from Mars to Earth, because Mars cooled faster and would have had more time to develop life, but it's also considered going star to star. Star to star is much more difficult, but less so in the birth cluster. As I discussed before, stars form in clusters, and while they're still in that cluster, they're closer together, and it would be easier for life to go from one star to another. So Adams and Napier modeled this process and concluded that interstellar panspermia could work, but not better than planet to planet. It only really works if life arises very quickly in the first place, so the explanatory power is significantly lessened. Planet to planet, panspermia would still be dominant. And also, for both cases, we don't really know about the biological limitations. How easily could life survive getting blasted off a planet's surface and survive the trip through interplanetary or interstellar space? So, not really a new development there, but it's good to put these kinds of bounds on the possibilities so we have a better idea of what we're looking for.